Hey, we're group 13. We're going to be presenting separation of an azeotropic solvent mixture via extractive distillation utilizing benzene and glycerol in trainers.
Water and isopropanol solutions are often produced as wastewater from other chemical processes. Isopropanol is an important organic substance used in manufacturing and also in households. One important use for it is that it's often used as a chemical intermediate for numerous chemical reactions. And because of this, isopropanol is readily available and easy to access, but it must be separated from the other mixtures. Due to isopropanol's importance and wide range of usage, it is important to separate the isopropanol from the water. An azeotrope is formed when components have the same vapor and liquid concentration at equilibrium. Because of this, distillation through vapor-liquid equilibrium is not viable for an IPA and water mixture due to the azeotrope present in the system. Thus, we will have to use extractive distillation. This means that we will be using solvents called entrainers to selectively attract components within the mixture. A good entrainer must have a high boiling point, low volatility, and not form an azeotrope with any of the components in the mixture. This figure shows vapor and liquid equilibrium data for isopropanol and water at 1 atmosphere in terms of mole fraction isopropanol. The blue line shows the vapor and liquid equilibrium data, and the orange line shows the line x equals y. As you can see, the azeotrope occurs when the vapor and liquid equilibrium data curve crosses the x and y line, meaning that the vapor and liquid compositions are equal. This means that the separation is unable to be done through simple distillation. The purpose of this report is to set up an extractive distillation column using Aspen Plus to separate the isopropanol and water system with glycerol and benzene as entrainers, and evaluate the cost and safety analysis associated with this system. The conditions are as follows. The feed stream is at 25 degrees Celsius and 1 atmosphere at a concentration of 40 mol% water and 60 mol% isopropanol. Our desired product purity is 98 mol% isopropanol and 99.9 mol% water. Our desired percent recovery is 98% isopropanol. And our entrainers are benzene and glycerol.
All right, so in determining the separation scheme, the first thing we had to look at was the thermodynamic model that we selected from the options in Aspen Plus. So we selected the activity coefficient based non-random to liquid model. And the reason for this is we have a lot of polar compounds, and we also have to be able to model liquid-liquid equilibrium because it's extractive distillation. And so activity coefficient based models are much better at this than other models. And then based on the literature and based on the CME 415 coursework, the NRTL was deemed the best model. And so we're looking here to reduce various costs that can be represented in various ways in Aspen Plus, while still meeting all the purity standards that Megan mentioned. And so in order to model in Aspen Plus, we had to do it step by step, developing one column and then meeting that with convergence, and then adding a second column or other equipment, and then finally adding in a recycle column. That way we did not deal with non-convergence in the system. And so sensitivity analyses were used to optimize all of the system inputs. And so then it was each of the parameters was adjusted accordingly to what the sensitivity analysis showed. And then for the glycerol system, we'll look at in just a second, 2 rad-frat columns were capable of effective separation. This is because glycerol has a very high boiling point as compared to water. as well as it does not form, it does not separate from water because of their traction. So a settler or decanter can't be used in the system. And instead, a second column can separate those. And so what was found in the glycerol system is that the distillate fractions of the two columns was kind of the greatest determiner in getting a system that converged and was effective at the separation. So that's where we saw the most sensitivity. And then some important parameters was, so increasing the feed temperature obviously has associated costs, but it was also detrimental to purity. And so it was most effective to leave the feed temperature at 25 degrees Celsius. And then also for this system specifically, the makeup flow rate of the solvent could be reduced to very low levels, as that helped both purity and obviously brought down costs by reducing the necessary flow. And then for the stage information, so the feed stages and the number of stages of both columns, we ran multivariable sensitivity analyses to observe the effect of the combination of those inputs on the purities as well as the utility costs. And so what we have on the right here is kind of the final sensitivity analysis, which was a reflux ratio on the extraction column, so the initial column. And so it's very clear here as we reduce the reflux ratio, it kind of reduces the total utility cost for the system. And then the lowest that can be reduced while still meeting our purity standards was 3.1. As you can see, as you get below that, the isopropanol purity does not reach the standards. And then the benzene systems, which is our other entrainer, would not reach convergence. The initial column by itself would only reach convergence if benzene was input at very high flow rates. And so in that situation, the bottoms was almost completely benzene. And so there was no separation whatsoever of the isopropanol and the water. And so at a variety of parameters, that system was not able to converge in Aspen.
Okay, so this is our flow sheet for glycerol. As you see, the feed and the solvent go into the first ratified column. The bottom feed of column 1 enters the feed of the recovery column. The isopropanol is separated from the extract column. The water is extracted from the recovery column, and then we have the recycle stream coming from the bottom of column 2 back into the feed of column 1. Okay, so the problem statement asked for certain specifications to be met, as JJ mentioned, and in order to meet those specifications, we had to have a reflux ratio of 3.1. There's 20 stages. There's a condenser temperature of about 82 degrees Celsius and a reboiler temperature of about 132 degrees Celsius. The recovery column had a reflux ratio of 1, had 9 stages, condenser temperature of 99.7 degrees Celsius, and a reboiler temperature of 287.4. So the reason benzene wasn't able to converge is because benzene and isopropanol have very similar boiling points. So by raising the temperature in the column, it would instead boil off benzene before isopropanol, so we weren't able to successfully separate the isopropanol and water. The glycerol, on the other hand, we were able to successfully separate using Aspen. As Jay said, we used the NRTL equation of state, and Yeah, we just were able to separate it using the conditions that we used finding the sensitivity data analysis.
Regarding process economics, there are various possible solutions to obtain the same desired product. To determine which process should be used, it's important to consider all economic aspects of each process. As previously seen, when glycerol is used as the entrainer for the separation, 2 columns, 2 reboilers, 2 condensers, and a recycle stream were implemented. It was found that this process would result in a total yearly cost of approximately $6,561,170. Majority of this cost comes from the capital cost, which is over $4.5 million, with the other almost $2 million coming from yearly operating costs for this process. However, this cannot be compared to the total cost of the process using benzene as the entrainer due to the lack of convergence. Instead, we had to compare the unit costs of benzene and glycerol. Currently, glycerol is roughly $100 per kilogram, while benzene is $10 to $50 per kilogram, meaning glycerol is a more expensive chemical than benzene, but no other conclusions can be made at this time regarding the process economics. In terms of process safety, it's important to analyze the safety risks of both glycerol and benzene as the solvents in the extractive distillation process. Benzene has been found to cause eye, skin, and lung damage or irritation if directly exposed, resulting in recommended personal protective equipment such as gloves, coveralls, respirators, safety goggles, face shield, and boots. Benzene is also highly flammable and poses a risk for fire and explosions indoors, outdoors, and in sewage systems. Benzene's extensive health and safety risks extend not only to those directly managing it, but to the environment and surrounding societies. As a result, benzene's waste must be incinerated or disposed of by licensed solvent recycling or disposal companies. If mishandled throughout the process or in storage, benzene can result in serious injury and or fire explosions. Glycerol, on the other hand, is deemed a safer class of chemical and is even used in many consumable products. There is little to no health concerns when handling glycerol, which results in no recommended personal protective equipment when handling this chemical. In addition, glycerol poses no environmental safety risks, and glycerol waste can even be disposed of by environmental biodegradation. Overall, glycerol poses little to no safety concerns throughout the process to the environment or to surrounding societies, whereas benzene poses a high health and environmental risk.
So in conclusion, the separation of isopropanol is one of the more important separation as chemical engineers. There are a variety of uses for isopropanol, so being able to successfully and inexpensively separate in order to achieve like relatively pure isopropanol is really important. And we need to like make sure we keep the cost down. We need to make sure we successfully separate the isopropanol from the water in the system. So like we said before, we used extractive distillation methods on Aspen, and we weren't able to separate using benzene because of the physical properties of benzene, but we were able to successfully separate using glycerol as an entrainer because glycerol had a really high boiling point and met the qualities that you would like from an entrainer. A glycerol entrainer system is successfully met.
Thank you for listening to our presentation on extractive distillation.